Okay, let me talk a little bit about exercise 9.4.6. This talks about the set capital T. Now notice this is a set and not a complex number. The set T is defined as the subset of the complex numbers whose elements all have modulus 1. That is, T is the set of C in little c and big C such that the absolute value of C is equal to 1. Now if you drew this set in the complex plane, this would look like a circle. This is the unit circle in the complex plane. How many points in the unit circle? Well, a whole bunch. In fact, there's an infinite number. So hold that thought, we'll come back to that later. Part A, using proposition 9.4.5, prove that T is a subgroup of C star. Proposition 9.4.5 has three conditions. First, you have to show that the identity element is in the set T. Then I need to show that the set T is closed under the group operation, which happens to be multiplication. You can tell it's multiplication because it's C star. C star means that there's no zero in the set. If there's not a zero, it must be a multiplicative group. Whenever you see a star, that means it's a multiplicative group. The third condition is you need to show it's closed under inverse. So this is going to be multiplicative inverse. So again, I said, notice that C star is a multiplicative group. We've already proved this, so you don't need to reprove it. We just need to prove these three conditions. All right, condition 1. We have to show that the identity is in T. Now, the identity for C star is the number 1, or 1 plus 0i. It's the same thing. Now, the condition for membership in T is that the norm, or modulus, or absolute value of the number is equal to 1. The modulus of 1 is indeed equal to 1. So 1 is in T. That verifies the identity property. So we're okay with number 1. Number 2, we need to show that T is closed under multiplication, our group operation. So let's suppose we have two elements of T. We call them Z and W. By the virtue of the fact that they're in T, their norms or absolute values are equal to 1. So we want to show that ZW is also in T. To be in T means that its norm is 1. So let's verify that the norm or modulus of ZW is 1. Well, the modulus of ZW is equal to the modulus of Z times the modulus of W. You can go back to chapter 2 to see that that's true. Modulus of Z is 1, modulus of W is 1. 1 times 1 equals 1, so the modulus of ZW is 1. ZW is in T. Third condition, we need to show that it's closed under inverse. So let's take an arbitrary element Z in T. That means that modulus of Z is equal to 1. So what about the modulus of Z inverse? Well, modulus of Z inverse is 1 over modulus of Z. This also comes from the same exercise 2.2.22. It's actually 2.2.22h. Let me see if I can write that here. This is 2.2.22h. So, and the modulus of Z is 1, so the modulus of Z inverse is equal to 1. I mean, Z inverse is in T. We verified the third condition. So that takes care of part A. We verified the three conditions. All right, so let's go on to part B. What is the order of T? Now notice that when you have these bars here, this does not mean modulus anymore. Modulus applies to a complex number. The bars mean different things in different contexts. It depends what you're applying the bars to. The bars applied to a set cannot mean modulus. It means the number of elements in that set. Now, how many elements in that set? Infinitely many. So that means the order is equal to infinity. That's the correct answer. Part C, prove or disprove that T is commutative. Well, T is a subgroup of C star. I shouldn't just say subset, I should say subgroup. So let me erase that. So T is a subgroup of C star. And C star is commutative. Now, if the bigger set's commutative, the smaller set is also commutative. So automatically we get commutativity from the fact that C star is commutative. And that's it.